Testing, testing. Yes, we're here. All right. Good afternoon, everyone. How's everyone doing? Choo. Are you ready for some parametric modeling? Okay, we're going to start. Are we going to start? Yes, I think we're going to start. Let me set up a couple things here on my end. And which are those things going to be? What are these things going to be? Whoa. Wait. No, that's not what I'm looking for. Is this what I'm looking for? Huh. Nope. Is this what I'm looking for? What am I looking for? What a great question that is. What are we all looking for, huh? Here. I think this is it. Great. And this is, oops. Okay. All right. Yes, I think this is what I'm looking for. Okay, well, sorry. Hi, good afternoon, Ali, Rolando. How's everyone doing? Faces to remove from close. Where's the shell one polysurface? Unselected. I'm not sure. With all faces selected. Huh, I don't understand what is going on. The result is not solid. All right. Oh my God. So wait, so I am trying to. Okay. Oh wait, so it's close underneath. Screw you. All right. From closed poly surface. Okay, to remove from, leave at least. Okay, so the face to remove. Okay, so that's the one. The result is not solid. Oh no. Uh-oh, so this is not working. That kind of sucks. Okay, what if I make it thicker? That one. We are not getting a nice result. Well, it's actually not that terrible, is it? The result is not solid. So here is kind of, all right. So except for this face here, but everything else is actually being shelled properly, no? Oops, oopsie. Good afternoon, everyone. So, what is going on? I am trying to create like a complex form because I'm going to do an exercise of cutting this in sections. So I just want to give it some thickness, basically. So I just want to, I select faces to remove. the result is not solid. Why is it not solid? Ah, this face is being annoying here. That sucks, but the rest is actually pretty neat, no? What is wrong with this face here? I wonder if I can... probably I cannot. This is not going to be... I wonder if I can remove this face and continue untrim the surfaces. Yeah, I know what you're saying, Ali. You're right. But I think there's something wrong with this face or with the intersection with that face. I don't know. But it would be super neat if we could do this. Why don't I just create like a similar surface, basically? I mean, how does it matter anyway? So, what is this? So I'm just going to do the following. I'm just going to create something that looks more or less the same. Something like this, and then something like this, then something like this, and then something a little smaller like this, and then here I'm going to do like a nice one. Oops, no, here I'm going to do like a larger one, and here we are going to do a larger one here, and then is this going to give me problems? Probably, right? I'm just going to leave that there. Or here, for example. And then I am going to, I am going to take all of this and say Boolean union. And then I'm going to add everything together. And then I'm going to make a really large box. And then Boolean difference. And then this minus this. And then boom. And then let me try to shell this thing. And we're going to move this face. Ah, why are you not solid? Why is it not? It is solid. I mean, it looks pretty solid to me, no? It looks great to me. What is so not solid about this? We're keeping this. It doesn't matter. Okay, and ghosted. Yes, there you go. And you're out of here. Yep, that's going to be it. Practice to shell them separately and then trim them all. That is not a bad idea, Ali. That is not a bad idea. You are right. But too late. I think it's already working. So, all right. So, I forgot. Hi, this is Jose Luis, Parametric Camp. We do computational design. Follow us on our social media. We have a Discord server. There's a link here in the description of this video. And we are finishing a list to here, which is we're going back to we're going to go back here, and then what are we going to do? What we're going to do today, this afternoon, is we are going to do an exercise where we're going to practice intersections, and then basically the exercise is going to be taking this thing and cutting it in a bunch of slices, and cutting it in a bunch of slices. Yes, cutting it in a bunch of slices, and then taking those slices and flattening them. So I have not done this exercise before, so it might be a little bumpy, and I'm going to bring in a sketch. So now we're going to do a sketch. And how are we going to do this? Well, how am I going to explain this? I'm just going to do an exercise where we're going to take we're going to take, well, the simple version is going to be just taking circling, just the simple exercise is going to be, we have whatever geometry, that was really bad, and oh, that really sucked. Wait. No. Okay, and then okay. So basically, the first way we're going to do this is we're going to have a line. We're going to draw some kind of line. We're going to subdivide that into a bunch of vertical planes, for example. We're going to subdivide that into a bunch of vertical planes. Each one of those planes is going to be then each one of those planes will be the intersection plane. I'm actually going to change the order of this thing. It doesn't matter. Nah, I'm not going to do that. It doesn't matter really. And then each one of these planes is going to generate an intersection. Each one of these planes is going to generate an intersection. And then that intersection, we will here, we will start laying those intersections, like something like this, something like this, something like this, in a series of target planes that we are going to have somewhere. And we're going to generate a bunch of planes like here, 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 and here. And we will just map those over there. And that's going to be the simple version. The advanced version will be making things a little cleaner. Making things a little cleaner. I'm going to explain that in the video. So let's just start recording, I think. Where are let's get started. So what we're going to do in this exercise is that we want to imagine that we have some kind of like generic shape. So we're going to imagine that this is some kind of building, for example, and that we want to extract the sections of the building, or it can be an object and we want to extract the sections of the object for making it or for fabricating, whatever that is. And this is going to be some general shape. Imagine that this is a blob or whatever that is. The process that we're going to follow to extract a series of sections from this object is going to be actually extremely straightforward. We're actually going to do it in two different stages. the simple, fast, quick, and dirty way of doing this is going to be just, for example, creating some kind of axis. So it's actually going to be probably a line, just a simple line. I'm going to take that line and subdivide it into vertical planes. So that's also going to be super easy to do. Then I'm going to use each one of those planes as a section in plane that is going to cut through the object that I have. And once I have all those sections in the 3D environment on top of the actual geometry, then I will do a simple reorientation process like we've done in previous exercises. Well, I will create a sequence of straightforward planes on the XY, and I will reorient each one of the sections back onto the floor on XY. Again, because these will be very useful for drafting plans, for sending this for fabrication, whatever you want to make out of this. It's a very common process to do. I'm saying that this is the quick and dirty version because it involves stuff that is not very parametric, like for example, drawing this line manually and cutting it and then generating planes that are like at regular intervals. But the second part of this video will be, I will try to make this process a little cleaner by making sure that the planes that are generating the cuts for the building are parametrically bound to the object. So they don't have like, you'll see what I mean by that. And then I will also make another optimization, which is the fact that all the planes that the sections are going to reorient to on XY, instead of being at regular intervals, which may leave larger or smaller gaps between the drawings, I'm going to make sure that the distance between them is actually fit to the size of the section, so that we have a more homogeneous distribution. I will also show what that means very soon, okay? Now let's go back to Grasshopper and let's get this part done, which is going to take us like a couple of minutes. It's super easy to do. All right, good afternoon, everyone. We started really quick, so I didn't get to say hi. Ali, Rolando, Hania, good to see you again. Engineering architecture, good to see you. Smith, welcome back. You've been following a lot this series, huh? Good to see everyone. Now, we have here the shape. I'm going to enter a B-rep here. I'm going to put here, and then I'm going to set here a curve. I'm going to input a curve here. This is going to be a straight line from here to here, for example. And then number of sections. That's going to be, for example, 20. I don't know. What else do I need as a parameter? I don't really need anything as a parameter, do I? No. Okay, let's do this then. Abdo, have we met each other before? I'm not sure, but welcome to the channel. And Dr. Manuel. Majestic name. Good to see you. Okay, let's get started. And then what we're going to do is I'm going to import that. I'm going to show the shell underneath. And what else are we going to do? I'm just going to import the lines, subdivide it in points, put vertical planes, and then just do the intersections. And then after that, the second part will be just putting those flat on the surface. And I'm going to distance between drawings. Okay, so which is going to be something like this, and also something. Okay, and then I'm going to save this somewhere. This is going to be E20. What is this going to be? Sections, for example, and this is also going to be E.section. Okay. And I'm going to do, okay, so I think we're ready. Let's go. So here we are back. We have some kind of geometry, some kind of complex form that we want to extract the sections for. I created basically this igloo-like kind. It's like a really fancy igloo of sorts, right? And I want to highlight that it's actually hollow. So it has kind of a wall thickness to it, which is going to make the sections a bit more interesting. And I also have this one straight line perfectly parallel to the y-axis that I'm going to be using as the axis for the vertical planes. So I have already dropped here a brep empty parameter box that I'm going to load with this geometry. And remember, just a reminder, this is just one single object. Everything is joined together as part of a Boolean operation. And then here, I'm going to join and I'm going to bring in the curve that I'm using as the axis. Okay? All right, I'm going to stop this and I'm going to hide this. And I have two sliders representing the amount of sections that I want to cut the building on and what is going to be the distance between the drawings as soon as I drop them here on the XY plane. So this is going to be extremely easy. So the first thing that I'm going to do is I'm going to subdivide this curve into vertical planes that are going to be the sectioning planes. So I can go here to division and I'm going to try perpendicular frames, for example, and I'm going to try that. I'm going to say curves and I'm going to say these are the amount of sections. But remember that when I divide a curve into a set of segments, what I get in return is one more plane than the segments. So maybe what I can do is I can do like a quick expression here where I say what I actually want is to be really precise. I want x minus 1. So if I want 20 sections, I need to divide the curve into 19 segments. So that's one thing. Okay? And you can see that I have now 20 vertical planes, and but I do not like the orientation of the planes. You can see that the orientation is like X is pointing up and Y is pointing to the right. I'm not sure that I like that orientation because when drawing it, it's going to be a little messy. So what I'm going to do is I'm just going to remove this and I'm going to create those planes manually myself. So I'm going to subdivide the curve into I'm going to subdivide the curve into a family of 19 segments, and then I'm going to place an XC plane on top of each one of these points. So you see that now the plane is oriented with the X to the right and with the Y pointing up, which I think is a nicer orientation. So then I have my planes. I'm going to use these planes as the sectioning planes for this brep. So now I'm going to go to intersections and I'm going to go to mathematical and I'm going to see that I have brep and plane as intersections. So I'm just going to drop this one and I'm going to create the intersections between this brep and all the planes that are contained here in the sectioning planes. And as I do that, you're going to see that I am getting all the sections for each one of these elements here, which is kind of nice. Let me hide this and you can see how if I had the planes as well and if I had all those points, you can see how I have all those sections in 3D, which is kind of nice. I like this. I actually like this a lot. Yeah. So now that I have these sections in 3D, what I want to do is I want to bring them into XY. How can we do that? The way I can do that is by taking, for example, I'm going to create a point. Oh, we have a point here. I'm going to create a point. I'm going to bring it into Grasshopper, and then I'm going to use this point as the center for an XY plane. Okay, and then what I'm going to do is I'm going to create a one-dimensional array of these planes in this direction. So for that, we also already know that one technique that we can use is to move this plane with a collection of vectors that are at increasing intervals. So for example, if I have 20 sections and if I have the distance between the section being 10 units, I can create a numerical series that starts at 0, that has the step size is how far away they are, how many elements is the amount of sections, and then this is going to give me a list of numbers that looks something like this. And if I use those to factor a unit y vector, then what I end up getting in return is a collection of y vectors multiplied by each one of these lengths, and therefore all the vectors for the motion. And now I can just take this and take this, and then I can now move the original plane by this collection of vectors, and then I get all these vectors for the sections. All right, and now I have the original planes, I have the target planes, and I have the sections that I want to move. So I can now reorient all of these elements with a simple Orient transformation. So I'm going to go to the Transform tab. I'm going to go to the Orient category. I'm going to place this here. I want to move all these curves, the sections. I want to move them with this being the reference plane and with this one being the target plane. And ta-da! So what is going on? Oh, something is not right here. All right. What have we said before that we need to take a look at when something is not working exactly the way we want? What is probably the culprit? Who is guilty for this? There's probably some data problems going on. So let's take a look at the data here and how can we fix this. Okay, so let me take a look first. So this is 20 elements, this is 20 elements, and this here is 20 branches. Okay, so I think if I graph this and if I graph this one, we should be good, right? Yes. Okay. All right. Now, what is the very first thing that we always need to do whenever we have data problems? We need to take a look at the data. So I'm going to place a panel here, and I'm going to take a look first at what's coming in from this plane. So this plane is a data tree structure that has one branch and 20 elements on the list. So that's one thing. The other thing is the other planes that we're working with are following a very, very similar structure. So these two should be good, I think. And what about what's coming out of the component? And also, why is this red? Why is this giving us an error? And why is this saying that the intersection failed? Well, the reason why this is saying that is because, for example, this plane here and these two planes here are not cutting anything, you know? And actually, if I were to plug this in here, you can see that the structure of the data is kind of very interesting. What we have is a data tree where instead of 20 elements, we have 20 branches in this case. And then each branch contains one closed planar curve or two closed. Can we have two closed planar curves? Where, for example, there are situations where here we have two curves, here we have two curves, because the result of the intersection might be more than one curve. And we also have branches that are empty, branches that do not have any data, like the first one, you see the first one, and the two last ones here. That is because the plane did not intersect with the object at all, and therefore no curve was generated. So now that we see that this is a structure, these are the structure of the curves, and this is the structure of the planes, what do you think from those two main data tree operations, which ones do you think we should try to go for? I'm going to give you a few seconds. You can pause this video if you want. I'm going to give you a couple seconds. Think about it. Think about it. Think about it. Tick tock, tick tock, tick tock. Well, we have the two options, okay? So we could flatten everything. So we could flatten this and give and remove all the complexity of the tree. However, in this case, I don't think that's a good idea because it turns out that we have a different amount of sections than we have of curves. So here we have 21 curves, whereas here we have 20 sections. And that's not going to be a good thing. And also, we also have a situation where some of the cuts don't have a section, so there should be nothing on there, and some of them have two things. So flattening is going to mess things around. So I think in this case, it might actually be better if we take each one of these two data trees, if we graph them so that every plane has its own branch, and then Grasshopper knows that the first branch of planes needs to go with this empty one, the second branch of planes needs to go with this curve here, the third branch of planes needs to go with these two curves here, etc., etc. So that would look something like this. I'm going to graph this, and then this becomes the new tree. I'm also going to graph this, and this becomes the new tree. And you can see that the structure of the data now looks very, very similar. It looks identical, and that each curve here or each group of curves is going to have a matching plane here and a matching plane here. So now I think with those two, now we can now say here and here. And did we get it? Woohoo! Yay! Hooray! It's looking great. And we have the two last planes are empty. They don't have any projection. And this first one here also doesn't have any projection. All right. So that was neat. That was very cool. I think this, and I'm going to clean this up a little bit. Yes. So actually, no, but before we do that, I'm going to keep this tree here because this is a very interesting tree that we're getting here. It's like a very non-standard one. So I'm going to keep it here because I like that we had exposure to that. So you can see that how easy this exercise was. It was basically, what is it, 10 components that we have used? It's like a super, super easy thing. I'm going to group these ones. I'm going to group these ones. And then I'm going to move here, here, and then I'm going to do here. I'm going to group this as well and group here. So the simple version of this exercise was this. But now what I want to do is I want to improve this exercise in a couple different ways. So for example, we did this straight line, but the nice thing about parametric design is that that line, there's no reason why it should be straight. So what if we wanted, for some reason, I don't know why we'd want to do this, but what if we wanted to find the sections that were kind of like this, you know? The sections of the building that were sort of like this. We can just plug in here the curve. We set this curve, and if we want to make them parallel, then that can work that way. Or if instead we want to make sections that are perpendicular to the actual curve, we can go back to the method that we were using before. So I'm going to plug in here the curve. I'm going to plug in here the amount of cuts, and then I'm going to use these frames here to fit this. And you can see how the cuts are now kind of all wacky and are following the perpendicularity of the curve, which is kind of cool. I'm not sure how useful this is, but it's kind of cool. And what's nice is that the orientation of the planes ended up being really nice as well. So we have here now these planes all the way here. So that is working well. However, I'm going to go back to the straight line just because, that's probably a more realistic scenario at this point. And this one and this one. So that's something that we could try. But most importantly, what I would like to try is to improve this exercise for the following reason. As you can see, the way we have done the line here, there's like a few gaps here. So there are planes that don't have sections. And I would like to make a definition that guarantees that we always have cuts. We all have sections because the sections are fitting perfectly the boundary of the object. So that's one thing that I'm going to do. The other thing that I'm going to do is the fact that if I look from the top view, you can see that this section is kind of small. These ones are also small, so there's a lot of gap here. These ones are bigger, so the gap is not so much. So if I could maybe shrink this, but now I'm shrinking all the way to the maximum and I still have a big gap here. So maybe what I want to do is I want to distribute these planes so that their distance is not always the same, it's different, but that distance adapts to how tall that section is. And maybe even add a little bit of a margin. That could be interesting, so that we get like a more fitted, like a more like a distribution of these sections that is according to how big those sections are, not to just some arbitrary number that we set. So follow me up, because I'm going to extend this exercise and I'm going to improve those two aspects to make everything a little more parametrically tight, which, as you know me already, I like those things. Let's take a look at the whiteboard and how we could make that happen. Rosalotus Mystic, how are you doing, sir? Andres, good afternoon. Andres, I'm still waiting. Okie dokie. So how are we going to do that? I have no idea. How are we going to do that? Oh, Rosalotus Mystic, are you a fanboy of PCs, of personal computers? Me too. I do not like Macs. Okay, so I know, I'm joking. I know, I hope you mean parametric count, because I would be grateful. Thank you. Okay, whiteboard. So what are we going to change here? So what is my mouse? Here. So I'm going to turn a few things off. I'm going to turn a few things off, and then what I would like to show is that what we're going to do in this case is that we're going to use a bounding box. Exactly, Ali, you're guiding it. We're using a bounding box, and then we're taking one of the wires, or we're finding the center. Yeah, and then we use that as the curve. Very good. Good thinking. So I'm going to make a bounding box, and I'm going to do it with the pen so that it's, oops, sorry. Uh-huh. And then after we do that, there's a couple ways we can go. We can just take, for example, this axis. We can take, for example, this wire here. We can take, for example, this wire, and then that is the wire that we can subdivide into planes So that's one thing. Or we can also do an operation where we take them from this. No, we're going to use that one. Yes, we're just going to do that. So that's going to be one thing. Mm-hmm. So, piece of cake, super easy. Remember how we said that we just took this arbitrary line that we drew and then we used that to generate vertical planes and cut the sections of the surface? Well, we're going to forget about that. Oops, sorry, I don't know what I turned on. We're going to forget about that and we're going to follow a more parametric way, which relates to generating those planes in a way that has a better logic depending on the shape of the object. And the way that we're going to do that is that we're going to find this thing that is called the bounding box. The bounding box is basically a box that is fitted to exactly the shape, exactly to contain absolutely, but in the most minimal way, a particular geometry. What that would mean is that the sides of the box are going to be touching the edges of the geometry on the x and y and z directions, and therefore it's going to be fitting it perfectly inside. And then once we have that box, then it's just going to be as easy as choosing one of the edges and then subdividing that edge into planes so that the first and the last plane are going to be perfectly tangent to one of the ends of the drawing, but all the rest of them inside are going to be cutting the geometry. And then once we have those planes, we feed those planes into the rest of the definition, and then we're good to go. So we're going to start with that, and then we will talk about how to move the planes to XY. Good afternoon, Parisa. How are we doing? I'm going to turn all of this off. I'm going to turn all of this off, turning this off. I'm going to disconnect. And then let me try something. So we have here the bounding box. Where is the bounding box? Bounding box. No? What? Where is the bounding box for a surface, folks? Wait, so bounding box is just this, right? So this works for B reps as well, no? Yes. Geometry to contain per object. Okay, and then we're going to have a box, a line, a box, and then we're going to, I don't know, deconstruct the box, for example. And we get domains. Now, we're going to take the B-rep edges. Now, we're going to take the box corners, deconstruct V-rep. It's going to get edges. Okay. Box, we can do box corners probably. It's going to make things a little easier. And then which one is going to be the one we want? So that's going to be A, B, C, and D. Which one is D? Huh. But that's weird. That's a very strange order. Well, maybe not so much. Okay, so that's going to be a line between A and B and D, and then we just plug that in here, and then we're good to go. Okay. Alrighty. So let's try that. Box wireframe. Is already the box wireframe? Oh. Oh, what? Sorry. Bounding box. And then it gives me the wireframe. Yeah, but now I need to cherry pick from this. I need to cherry pick which one is the one line that I want, right? So I would need to just take the list item and find out which one it is. So I can talk about that. Mm-hmm. Mm-hmm. I'm going to make the planes a little smaller. Okay. So back here in Grasshopper, I have turned off all the other geometry, etc. And I'm going to focus here only on this one, on the geometry. I'm going to show the B-rep here so that we can all see it clearly. And actually, now let me hide it from here and let me turn it on here so that we can see it a bit more clearly. Correct. And then what I'm going to do now is, remember, I'm going to create a bounding box that is going to contain perfectly this object. The way I'm going to do that is that I'm going to go to primitives. And in primitives, we actually have boxes that are oriented in a way that it contains a particular geometrical object. So I'm going to click on bounding box, and you can see that the input is a geometry that I want to contain, and whether if we want to orient that box in a particular angle. So I'm going to stick with the global XY, which is going to be enough. And then you can see that as I plug that in here, you can see that this box is containing perfectly my object in, it's like touching in just with the one point at each one of the four of the six sides of the geometry. I want to highlight how this component, the input, is of the type geometry, so this swirly kind of hexagon here, and that is because we can create bounding boxes for B-rep, for surfaces, for curves, for a collection of objects, etc., etc. And here the output is a box. So now we have the box, and what we need to do is we need to figure out how to take, for example, this line here. If we go to analysis, there's actually a bunch of components that could help us here. We could, for example, use the B-rep wireframe, which if we plug a box, you can see that it gives us a list of the 12 edges, and then we would just simply have to use list item to cherry pick from this list the one that is the one that we want. So for example, let's try that out. So I'm going to say list item, I'm going to plug this in here, and I'm going to plug here I'm going to plug here. So you see how 0 is this one here, then 1, 2, and 3. So it would be number 3, the one that we want. So I would substitute this with a hard-coded 3 so that we know that it's always going to be that one. And then we could plug this in here, and then we already have all those planes and then all the sections for my building. So that could be one way to go. Another way to go about this could be, for example, could be taking box corners. So as I do that, and as I deconstruct the bounding box, I can get the 8 corners, and it turns out the corner, I believe which one it is. So point, let me see, I'm going to plug this in here so we can see that. I'm going to, where are the planes? I want to turn everything off. So we can see that point A is one of them, then point B is not, point C is not, point D is the other one. So I could create a simple line between A and D, and then I have the line that I wanted, and then I can plug that in here, and then everything is going to work. I have the planes, and I have the sections, and everything works exactly the same. There's no real advantage between one method or the other. Perhaps this one is like slightly more optimal because I don't have to generate 12 lines and then only take one. Any process that means generating a lot of stuff and then discarding a lot of stuff, in general, it's a little less efficient than generating. I mean, I'm generating 8 points here, arguably. So, but points are more lightweight than lines. It doesn't really make a difference. And you can see that performance-wise, I am not getting any one of these like I'm not getting any one of these profiler pop-ups telling me that this is taking like however many milliseconds. So we're good. So both are pretty much the same. So I'm going to go for this one just because I like it a little more. It's a bit more elegant. It's cleaner maybe. So I'm going to just keep this one here. All right. And then I'm going to plug that in here. And then I get my sections. I'm going to turn off this and my sections are there. And I'm going to turn off the planes and everything looks good to me. So now it's going to be a matter of figuring out how can I take these sections and lay them flat here in a way that they are respecting their relative heights. Let's go back to the whiteboard and figure out how to do that. Okay. All right, so actually, before we do that, let me figure out, because how do we do the bounding box of flat objects? The bounding box is just the same, right? They have the box, I have the box. Per object, union box. I want the union box. Is this how we're doing this? And then I guess I can measure the height, no? So I can measure the height, and C is going to be whatever from blah, blah, blah. And then I can calculate the domain length. Huh, how do I find the length of a domain? Interesting. How do I calculate the length of a domain? I extract and then just subtract things. Is it? This seems like there should be length domain. Measure the length of a curved subdomain. No, this no. And if I turn this into a number, then do I get the actual values or no? Oh, I do actually. 83 is this plus, interesting. Let's see if that is true. So if I move this all the way up here, yes, interesting. So if I turn a domain into a number, it just calculates the length right away. If I do, no, but if I do bounds, oops, sorry, if I do bounds, numbers to include in bounds. Oh, that is weird, but it gives me domains. Now, I mean, technically the way I should do this is by taking this and then subtracting from this one, subtracting this one. And that's the right way to do it. And then I can just, I can flatten all of this. I can do a mass addition to this. And then I'm going to find all the intermediate steps. Am I going to get in trouble with this? Let me finish this up because now I am not sure that. And then I'm going to graph this. I'm going to bound this. A height line? What is a height line, Ali? The mesh and the curve length. The mesh of the curve. Oh, I see what you mean. Yeah, I see what you mean now. So these are the closed curves. So now I just need to orient. This geometry from this to. Oh, and that's what I need to do for the length of this. And the distance are not correct. Replace nulls with zeros. I'm going to replace this. Okay, so that the item is 0. And then it's going to look like this. Okay, so I am going to use this. And then mass additions. Wow. Okay, so I think I'm just getting myself into trouble here. So actually the first one doesn't need to go because, oh God, this is going to be a pain to explain. Oh. And I need to actually shift this and set this to false. Yes, and this is what we plug in here. What? Oh no. I think I'm overcomplicating this. So actually, I don't need to do that. Oh God. Hmm. Okay, it's going to be more tedious than I thought it was going to be. I'm not sure if it's a good. Okay, well, I said I was going to say I was going to do it, so I think now I have to do. Now we have to figure out. Uh, okay, I think I just need to say that because the only problem that we have is that they're off by 1 unit, basically. That's the big problem that we have. So basically the problem is that we need to start 1 unit below. Okay, so let me let me redo all of this. So we have the planes. We have the sections here. And this is just one section, whatever. So the bounding boxes are there. Then these are the heights, and these are all the heights of each one of these elements. Okay? So what we need to do is we need to flatten this together, all of this together, so that we get this. Wait, how was I doing it before that didn't have? Because I was replacing the null items. Oh. Okay, I think I made a mess and I overpromised. It's not that this is not solvable, it's going to involve just a lot of explaining tiny things. So, okay, so let me do it first my way, and then we find a way to either make that simpler or easy to understand and to explain, and then we take it from there. So the problem is that we have I explain the problem. This is sucking big time. So we're going to replace this with zeros. Okay, that's fine. Then we get this, and this is the height of each one of the planes. Correct? So this is the height of each one of the sections. So what we need to do is that this is the height of each one of the sections. So what we need to do is we need to make sure that we have. I know it's messy, Ali, but I said I was going to do it already. So I don't think we can just not do it now. It's kind of not cool. And maybe this can be helpful for other people. So these are the planes now. So I'm just going to remove this here. And then what we need to do is that we have these are the original planes. And then what I need to do is I need to create a set of planes where the first one is for the second one. So I have to offset all the I need to introduce a 0 here. Merge, so I need to merge this, I need to introduce a 0 here, and I need to do here. And then here we do mass addition. Wait, what just happened here? And then here, what is the result? The result is this, and the output of this is all of this. Okay. So if I use this now to create y vectors and to move this stuff with these y vectors, I would create all of those, and then if I plug that in here, what just happened there? Oh, wait. No, I moved these planes here. Okay. And you see now it's solved, and now they are super nice. And if I actually move the boxes here, if I actually move if I do the same operation but I move the actual bounding boxes, we can see that everything fits perfectly like this. And to each one of these elements, I could just add a margin. To each one of these elements, I could just add a margin to space them out a tiny bit in between them. So for example, like this. So yes, so but now how do I explain this in a way that makes sense? This is going to be ugly. How do I explain this in a way that makes sense? Okay, because the first thing we need to do is we need to go to the board. How to do that? Very good question. Let's okay. So let me save this. Let me save this, and let's start a new one. And let's imagine that we have, for example, all right, so we have a slice, we have another slice, and we have another slice here. Okay, so let's simplify the problem. So that's one thing, and then we know that the first one is 1, the second one is 3, and the third one is 2 in height. Correct? So what I need to do now is I need to take a plane, take another plane, take another plane, take another plane, and take another plane. And as I do that, take because I want to do that with, because I want to draw here the first one. I want to draw here the second one, and I want to draw here the third one. And actually the fourth plane doesn't really matter. I don't need a fourth plane. I actually don't need a fourth plane, so that is a very good point. So after I do that, I want to say, well, what is the distance? What is the distance that I want to do? I want to say, well, the distance between them are going to be 1, 3, and then this one doesn't really exist. We don't care about that. So we still have 3 planes. And what we need to do is we can say now the list that we need to do, even though we have planes that are in a sequence, for example, we need to say that for item number 1, if the index of the element is 0, 1, 2, then the next thing that I want to say is the height of these elements is going to be 1, 3, and 2. Those were confusing numbers. And then the plane position. The plane position is going to be, the first one is going to be 0, the second one is going to be 1, and the third one is going to be 4. And there's no, and this one doesn't really matter. 4. What did I get myself into? Huh? I did not expect that when I was doing the exercise. Okay, so okay, so I think, is this enough to explain this whole situation? So this is going to be number 0, number 1, and number 2. It's going to be number 0. Oops. It's going to be number 0, number 1, and number 2. And this is going to be y direction, or y height. I may want to just explain this manually, right? So I may just actually draw this manually. Up from here, I may just want to manually just explain that as we go. Yeah, I may want to do that. Well, this I can use, but this one I'm going to definitely. Okay. Okay, so let me try to explain. Let me try to explain this. Yeah, exactly one way. Explaining things clearly is way more of a challenge than actually just sitting down and figuring out. Okay, so, okay, let's try this one. And then you tell me, please, in the chat, you tell me if the explanation made sense or not. And if the explanation made sense or not. And if we can try again in a different way. Actually, why don't I change these numbers? Because I don't like the numbers that I chose. So what if I change the actual numbers and I say, for example, what if I say that these numbers need to be, for example, this is going to be, this is going to be 3, this is going to be 7, and this is going to be 4, for example. And then, yeah, I think I really want to do that because otherwise numbers that look very close to indices are going to be confusing. The heights here are going to be 3, but heights here are going to be 3, cut. So this is going to be a 3, this is going to be a 7, and then this is going to be a 4. And then here, this is going to be a... What would I do without the sketching? I would be absolutely lost if I had to explain this verbally. And poor people listening to me explaining this verbally, right? Huh? That would be terrible. Okay. Are we ready for this? I have no idea. I'm not sure I'm ready for this. But we're going to try and see how it goes, okay? And, okay. Okay, let me try to explain this with a couple diagrams and buckle yourselves up, hold yourself up to the chair because I need your 200% attention because this might be a little confusing, okay? So bear with me. What we want to do is the problem that we have here is basically that we have a few sections in 3D space named from 0 to 2, for example. Let's say we have 3. And then what we want to do is, and each one of those sections may have a particular height. So it might be however tall in the C direction, that doesn't matter. So what we want to do is we need to figure out a way of arranging a collection of planes in XY so that the distances between them are so that these sections, when placed on top of them, they have the exact dimension, the exact C dimension between them here. So this dimension and this dimension are the exact dimensions for the height of this section and the height of this section, correct? So the challenge here is basically figuring out what are the distances between these planes and how do I create them. So that's what we need to find, okay? Now, it's going to be a little confusing because we need to do a little bit of like changing things around for the following reason. Think about this. Think about how we have the problem set up. We do have, we know that the planes are arranged between them. We know that if we have 3 sections, we need to create 3 planes. And we know that the distance between the first plane and the second plane equals the height of the first section. And we know that the distance between the second and the third plane equals the height of the second section. And for the last section, we don't really need another plane on top of it, so we don't need to care about that. Now, the question is, because I need to place these planes in XYZ space, what is the Y coordinate? What is the Y coordinate of each one of these planes so that I can generate a numerical sequence and then place this in space? So let's imagine that this plane had an I coordinate of 0. So we start from 0 and then we just need to figure out the y coordinates of each one of them, of the rest of the planes. The way we can go about this is by thinking that if we have 3 planes, each one of them having an index number, and that we know the height of each one of them, the challenge is creating a new set of numbers that is going to define cumulatively what is going to be the y coordinate of each one of the planes. So I can say here, I can go here and say, well, the y of the plane, how do I calculate that? Well, it turns out that for the first plane, I know that it's going to be 0, or whatever the original plane is going to be. For the second one, for the second plane, it's going to be the height of the previous one. So you can see here that for the second plane is going to be the height of the opposite section. So you can already see how we have to here add an artificial 0, which doesn't come from anywhere, and that the y-plane on the second position equals the value of the height of the first position. So you can already see how we're going to have to do some kind of shifting of lists, something like that. We'll see. But then, so the coordinate of this one is going to be 3. But then what is the coordinate of this one? The coordinate of that one here is going to be the addition of the heights of all the previous numbers. So 3 plus 7 is going to be 10. And therefore, the y-coordinate of this one is going to be 10. And if we had to place here another section, because this distance would be 4, the coordinate of this one would be the addition of all of this, if we had them, which we don't have it here, which would be 14. But you can see how basically each one of these numbers is the cumulative height of all the previous ones except for this one. You see? You see where I'm going with this? So, long story short, what are we going to have to do? First of all, we're going to have to create a list. Our target is to create a list of all the y locations of each one of those planes. And then we're going to first start with an artificial 0. And then we're going to have to do cumulative additions of all the heights of all the sections that we have on our sketch. So, I hope this was clear. I'm not sure how to explain it in a different way, but then maybe by watching how I do it in Grasshopper now, maybe we can get some clarity about that. Let's go to Grasshopper and let's figure out how to implement this that I just described here. How did that go? Ali, did you get lost? Did you get lost with this? No. Oh my God, no. One way. But was it clear? Was it clear? What do you think? Huh? Okay, so let's go to Grasshopper. And first of all, let's go here. Okay. A bit intense. Yes, I know it's a bit intense, but it is what it is. Yes. Okay, I'm going to do this very slowly, one step at a time. We're going to go back to the whiteboard, and this is the first thing that we need to figure out. We need to figure out first the height of each one of the blocks of the sections. So I'm going to go back to here. I'm going to hide this so that I can see the geometry a bit more clearly. And if I will, maybe I want to turn that on, or maybe I don't. Maybe I just want to keep the sections here. So the first thing that I need to do is I need to figure out the height of each one of the sections. So for that, I'm also going to use the boundary box. So I'm going to the bounding box. So I'm going to go to surface, primitive, bounding box. And then for each one of these, I'm going to calculate the bounding box. But this is not going to work because you can see that what I'm getting is like several bounding boxes per collection of sections. So for example, you see how for these two sections, I get two different bounding boxes. And I actually don't want that. I want one bounding box taking everything inside. So if I zoom into this component, you can see that it has this thing here called per object. So I can right click on the component and then click on this option, which says that when it's checked, instead of doing bounding boxes for every single object, it does one bounding box for all the elements that are inside of the list. Okay? So that is going to be, it's going to give me a data tree that has all the boxes, and each box contains all of the sections. All right. So that's great. And then I need to figure out the height. How do I do the height? Well, it's going to be not very complicated. There is in analysis, there is a component that is called deconstruct box. If I do that and I place this component here, you can see that it gives me like the plane for the box, but it also gives me the X, Y, and Z domains of the box. What does that mean? The domain means that the box is somewhere placed in XYZ, and therefore it doesn't just give me the length, it gives me where the box starts and where the box ends. And if I actually were to show this, and if I were to move the surface like farther up, you could see that it doesn't really give me the length, it gives me the Z coordinate of where the box starts and the Z coordinate of where the box ends. Because this is a domain, remember, that has a start and an end, what I can do to actually calculate the length is I can go to domains, I can deconstruct the domain, getting both the starting values, getting both the starting values, which are the same for all of them, and then the end values, which are different, and then just subtracting from the last element, subtracting from the last, the beginning, and then that way I'm going to get a list with all the lengths of each one of these elements here. Can you see that? Alrighty. One problem that I'm carrying, though, from the fact that the first and the last planes were perpendicular, were absolutely tangent to the geometry. I'm going to move this back down. From the fact that the first and the last planes were tangent to the geometry and therefore did not generate any kind of intersection, so the first one and the last one are empty branches. One problem that I'm still carrying from there is the fact that for calculations, the first branch and the last branch are always empty. Because if you look here, you can see how this box, for example, the bounding boxes for the first collection and for the last collection had null items here. This is going to carry me problems. I'm going to accumulate problems by the end. So what I would like to do right now is I would like to take this data tree that has some boxes and some null boxes, and I would like to replace those null boxes with some value that I can use later for calculation. So because what I'm trying to do is calculating the heights of each one of the section groups, what I'm going to do is here, what I'm going to do is I'm going to try to replace from these nulls, I'm going to try to replace them with the value of 0. So for example, I'm going to go here to lists, and you can see that there's a component that says replace nulls with other data. So I'm going to place that here in the middle. I'm going to take this as the input. R is going to be the item that I want to replace. So I'm going to do a hard-coded 0 here. And then you can see that the output is now a 0 here and another 0 on the last branch. I'm going to feed this now back to my calculations. And you can see that now my calculations have a 0 here and they also have a 0 here, which is very nice because it is true that for those sections, I do not have any height there. Okay? Wonderful. So I'm going to just to make sure that I'm going to make sure that these are clearly the section heights. All right, so this is what I got here, and this is how I'm calculating those sections heights, and this is correct. Okay, beautiful. Then what is the next thing that we need to do? The next thing that I need to do, according to the diagram, is going to be figuring out what are the y coordinates of each one of the planes. Okay? And this is because if you remember, when we generate the planes here in order to drop this, what we typically do is we take one plane, one original plane, and then we create a numerical series, and then we copy that plane by a sequence of numbers. All right? So that sequence of numbers now is whatever, but this one is going to be now the one that we are going to generate as the y coordinates, so the green list that I have in there. So how are we going to do that? I am going to copy this here. I'm going to create the xy plane here. Okay, and what I'm going to do is going to be the following. Remember that the list of y coordinates for the planes was, first, it was the cumulative heights of adding, for each one of them, adding, this is all the heights added, this is all the heights added, this is all the heights added. So it is a list of incremental additions of all those numbers. How can I do that with the section heights? Well, I could do that with for loops and other techniques that involve some coding, but it actually, here in Grasshopper, in operators, I have this really handy component that is called mass addition. What mass addition does is that it takes a list of items and it adds them all together. So what does that mean? Let me plug this in here and let me compare the inputs and the output. The result is actually nothing, because remember that components work at the list level. So this component is trying to add all the elements on this list, which is just 0, all the elements on this list, which is only 3, so the result is the same. So what I need to do is I need to flatten all these numbers into a one continuous list, so that when I add them together, the result is 77 point something something. But this result is very useless. What is super useful with mass addition is that the output also gives me the partial results of these additions, which means that for every calculation, it gives me the addition of this element and all the previous ones. So you can see how for 4, I get 7, which is 4 plus 3. 4, 4, and 3 is roughly 12. 5, 4, 4, 3 is roughly 17. 4, blah, 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 is roughly 22. So here I get that list of all the elements added one after the other. So that would be, on our sketches, it would be this list of elements here. Don't get confused by the fact that we have a 0 here. This is an unfortunate consequence that is going to make things very confusing, but this is just because the first section happens to not exist. So we have an additional 0 to deal with, but we still need to take our list of all the massively added numbers, and then we still need to add a 0 at the beginning. So how does that, okay, so let me actually not do that so that we can see how the error, how this would work. So let's say that I use these numbers to create all the vectors to move the planes. So I'm going to now use these numbers to generate the y vectors, and then I'm going to move this plane, the original one. I'm going to turn this off, sorry. I'm going to move this plane, the one that I use for reference, and I'm going to move this plane by all these vertical planes. And you can see how very nicely I have shorter, larger differences, and then shorter again, which kind of matches the fact that these sections are shorter, these ones are bigger, and these ones are shorter. So I think we are getting closer. Now, what I need to do is I need to now use those planes that I created here to do the orientation. So I'm going to orient all these planes, so all these sections, I'm going to orient them from their original planes to the new target planes that I have defined here, which are going to be these ones here. And you can see that I have something weird, a lot of problems here, and that is because if we look at the structure, remember these are all grafted, but the data that I have here is flattened. So I need to graft that data and I need to feed it in here, grafted. Okay? And you can see that it's already working. Except for the fact that you can see how this is not really working because there are some overlaps here. You can see that there is an overlap here. There are clearly some overlaps here. And there is a missing plane here. So that is, again, and if I do a parallel process, let me also flip not just the sections, but let me flip also the bounding boxes for the heights. So let me flip here all these bounding boxes for the height so that we can clearly see them. You see, you see, they have like these like serious overlaps on top of each other. So that is because I have not added this trailing 0 that I was discussing before here. So how am I going to do that? Well, here under mass addition, after I flatten the tree and I have all my numbers one after the other, I just need to add another 0 to the beginning. So what I'm going to do is I'm going to take this component that is going to merge two data streams together. And the first data stream that I'm going to merge is a single list with the value of 0. So that's going to be 1. And the other one is going to be this flattened tree. You can see that the result now is going to be the same list, but with a 0 on the beginning. And then, are you ready for this? Are you ready for this? And then as soon as I plug this in here, now all the sections are like perfectly set one after the other with the exact heights and super snug, like really perfect, like a really nice perfect fitting. Wait, but maybe it's too much. Maybe they're fitting too well. What if we added like a tiny bit of a margin inside of here? Well, that's just going to be as simple as taking all these numbers and adding like a small value to each one of them before they get added together. So here, before we flatten the tree, I'm going to add, for example, 0, boom, I'm going to add to these values, I'm going to add this, and then I'm going to plug this in here. And now we have this tiny margin that we can use to put them all together, or just to give them like a tiny bit of spacing between them, like 0.1, for example. And with that, I'm going to turn off this. I'm going to turn off the planes. I'm going to turn off like all this stuff. And I'm actually not going to turn off the plane. I like to see this. And I'm going to turn, what am I going to turn off? I'm going to turn this off. And I think with this, ta-da! This is what I wanted to get to. Oh my God, I can't believe it's taking us an hour and a half to get this going. Ooh. All right. So now I need to record the wrap up and I need to record the introduction as well. What about the section of the structure that thinks according to Y value? I am not sure what you mean one way. Okay, let me record the... Okay, I think this is where I wanted to finish this exercise. I honestly did not think that this part was going to be so convoluted, maybe, if you will. I don't know. But I think it was actually a really interesting exercise and a fairly advanced one on data manipulation and geometry conceptualization. Anyway, I hope this was useful. This idea of sectioning an element and laying it out in a way that it fits really well so that we don't waste material when laser cutting it or 3D printing it or whatever. It's actually a very common one. So I hope that was useful. Thank you very much. I will see you on the next videos on this series. More learning, more hands-on exercises. And in the meantime, maybe you want to like this video. Maybe you want to leave a comment. Maybe you want to subscribe to the channel. All those YouTube things that we do in modern world life, whatever. See you on the next video. Bye-bye. Thank you. Okay. I'm going to move this to the beginning. I'm going to move this to the beginning. And then I'm going to move this here. And then I'm going to move this here. Move this here. And move this here. And then I'm going to keep this here. Yes. Okay. Mhm. Mhm. Okay. Let's do selections. Mm, and then I'm going to do here curve. And it's going to be sections x and y. This is going to be whatever. And this is going to be section bounding boxes. And then I'm just going to okay. All right, I think I'm ready to record the introduction. Hi, this is Jose Luis, and welcome to another video on this series, Introduction to Parametric Modeling, where I'm going to do a hands-on exercise on taking some random input geometry, like some design geometry, for example, a building or some kind of object, whatever, and perform an operation where we're going to create a serialized way of slicing this object into planar sections. So we're going to cut the object into a collection of sections, more or less sections. These can be for fabrication, this can be for drafting plans of the object, whatever that is. And then once we have those sections, we're going to lay them flat on top of the XY plane so that they have the real dimensions and they could be laser cut, they could be cut into a model, whatever that is. I'm going to do this exercise in two ways. One is going to be like super quick and dirty. It's going to take me 5 minutes. It's going to be super easy to do. But the second version, the improved version, is going to take me a little bit more time because what I would like to do for the second one is make sure that the distancing between these sections fits a bounding box where the distances are not going to be equal but are going to be correlative to how high each one of these sections is, plus a little bit of a margin that I will be able to control. So that I can lay down those sections without wasting space. Okay, so that part is going to take me a little bit more time of breakdown because it's going to involve some breaking down of the geometrical relationships combined with some data manipulation, etc. So that part is going to be perhaps a little more advanced. So if you don't feel that you're there or you just don't want to sit down through 40 minutes of data matching, then just like just feel free to skip the second part of this video, okay? But this is going to be super interesting, and the quick and dirty version is going to be super easy to do. Let's take a look at how to make this happen. Alrighty. Oh God. Okay. Okay, so that was it. I'm going to remove this here. I'm going to clear this here. And this is going to be the version that is going to go. All right. And then here, I'm going to save changes. Yes. And then now template. Okay. Can I go get a glass of water? Can I please? We offset thickness of the curve, changing respect to the section box height. Maybe that's a way to go, but I don't know. I've already done it in that particular way. All right, so let me go get a glass of water. I'll be right back. Okay. Oof. Are we ready for more? Are we ready for more? Oh, I'm not sure if I'm ready myself. Okay. How's everyone doing? This one ended up being intense, huh? Why? How did that happen? I thought it was going to be. I remembered it being slightly easier. Maybe it's not. I don't know. Open Nest. Have I used Open Nest? I think I used it once. When was that? I think I used it a while ago. Open Nest, but I used it for like something a bit more complex. For like, I had like this like slicing thing and all these pieces, and Open Nest is really good at like laying things around and like snag. It was very nice actually, and much more complex than what we just did here. Yeah, but I should have mentioned that. You're right. I should have used the word nesting to discuss like um, how this is a way of nesting in a way. Yes. The code inside uses what's called heuristics, Andres. So what it does is it runs simulations and it starts like placing things and like moving them around slightly and computing how optimal the distance between things and to avoid collisions. And that's how it does the nesting. That's how it does the nesting. That's how it does the nesting logic. Yeah. All right. Oh, what do I have next? I have randomness. You guys want to do random stuff? We are going to do random stuff. Yes. Mm-hmm. Hmm. Okay, let's discuss randomness. Okay, so randomness. Okay. Mm-hmm. Okay, so how do we do randomness? How are we going to discuss randomness? Ended? What do you mean ended? No, we're not done. We're going to record more. We're going to I'm going to do a lecture on randomness, and if I have time and energy, I will do a small exercise. Okay. How can I start? So what are we going to do here? We're going to say that we just want to generate random numbers very simply. We're going to generate random numbers very simply. And then I'm going to show how to populate, for example, a rectangle with random numbers, for example, with random points. And then I would like to discuss a little bit conceptually about randomness and how creative it is. And then, for example, I would like to explain the concept of where things are coming from, and then how we have the seed. Yeah, so I would like to talk about the seed. And then for that, random numbers from atmospheric noise. And random.org. Atmospheric noise, and then lava lamps, earth flare, random number. So that's another one. And random number generator equation. sequence with the following sequence. Maybe I want to use this one. Random number generation. Linear congruential generator. Wow, that sounds majestic. Okay. Computational methods, random number generator, or the linear congruential generator. Okay. Okay, so I can talk about that. Yes, okay. But we can talk about that later. All right, so let's just get started. I'm going to do that. I'm going to place here. So, and then for the random numbers, I'm going to the domain of the numerical range, and then number of random values, and the seed. So then I'm going to start with a numerical range. So that's going to be 0, domain start, domain end, it's going to be the value of 1. And then I am going to create random numbers, and then, for example, 10 numbers. And then the seed is going to be some number like this. And then a panel is going to okay. All right. Let's do this. Hi, this is Jose Luis, and welcome to another video in the series Introduction to Computational. No. Going back. Hi, this is Jose Luis, and welcome to another video on this series, Introduction to Parametric Modeling. In this video, I would like to talk conceptually and with a few simple examples about the notion of randomness. And I would like to address that because randomness is actually a technique that is fairly common used when doing when doing modeling in general. And I would even go farther to say that sometimes it's even a little abused in my honest opinion, but it's nonetheless a really useful technique. And it is useful because many of the things that we model very often are somehow inspired by nature. And it turns out that nature, for us humans, has a lot of apparent randomness. Things are not ordered perfectly on a grid. They don't look so mechanical, so orderly. And that's why we feel that very often randomness is a technique that leads us to things that are a bit more nature looking or more nature inspired, if you will. At the same time, randomness had like a sort of stylistic period where random facades or like random distribution of colors, whatever, was a thing just to like spice things up and stylistically, if you will. I don't really know why that happened, but it had its moment. Maybe people are still using it and it has like some real world utility. And that's why I would like to talk about this conceptually and discuss how computationally randomness is typically generated, handled, and a few things that we need to keep in mind that are important when generating randomness. And for us, computationally, when I say generating randomness, what I basically mean is generating sequences of numbers, because at the end of the day, most of what we do in computational design is represented by numbers. So when we want to generate randomness, what we need to do is we need to generate sequences of random numbers that then we use for specific purposes. How can we do that, for example, in Grasshopper? Well, if we go to sets and if we go to the sequence tab, you can see that we have a lot of components that we haven't really taken a look at, but I really encourage you to check them out. One of them being the random component, which generates a list of pseudo random numbers. I will address what that pseudo means very soon. And if we look at the icon, you can see that the icon is this kind of cat inside of a box. Are you nerdy enough that you know what that it's a reference for? I'm not sure if you do, but that is a reference to Schrodinger's cat, or this metaphor that Schrödinger? Was Schrödinger or was it Feynman who did the metaphor? A metaphor about the duality of quantum states. That I'm actually not. I'm actually not qualified to actually explain that. I'm going to make a bad job. So just Google that. The Schrödinger's cat. Okay. Now, but the long story short was that the metaphor was about a cat that was inside of a box, and that while it was inside of the box, could be both at the same time alive and dead. But then when you open the box, then you randomly discovered whether if it was alive or not. But again, don't ask me why. Don't ask me why that is. Actually, I cannot explain that very well. So, but how do we use this component? Well, very simple. This component allows us to generate pseudo random numbers with a few particular inputs. For example, the first one is the domain of the range of numbers that we want to generate. So for example, I want to generate numbers from 0 to 1 with a domain. I also can select how many random values I want to generate. So for example, I'm going to generate 10 random numbers, and then I would like to be able to control the seed of the random engine. Let's put a pin on that one. Let's not care about that for the time being. But you can see that if I generate this, I generate a list of numbers that look random to me from 0 to 1. And if I expand this increment, you can see that the domain of this numbers generation expands proportionally. So before I had a range from 0 to 1, you can see that 77, 40, 16, and if I multiply the domain by 100, I still get 77, 40, 16, etc., etc. So you can see that this particular component, basically the domain, makes the range of those random numbers proportionally. How is this useful? Well, it's actually super useful because we can generate, for example, sequences of numbers that we can use to, for example, create a collection of random points. Let me show you how that is done. So for example, I have my first sequence of random points, random numbers that I have generated from 0 to 10, and this is going to be 10 actual numbers. And then I'm just going to copy paste this whole thing and then paste it somewhere here to generate a second sequence of numbers. That is also going to go from 0 to 10. Then because I want to generate the same amount of points, I'm going to use the same slider here. And then I have my sequence of random points, of random numbers here. If I now construct a point using this set of numbers as the x coordinates and this other set of number as the y coordinate, I should get some randomly distributed points in x and y. However, I can see that there is some randomness, but obviously this doesn't look random because they're all aligned across this one diagonal. Why is that the case? Well, it turns out that if I look at the numerical values of the x coordinates and if I look at the numerical values of the y coordinates, turns out that they are exactly the same. And even if I vary the domain of one, yeah, the numbers change proportionally, but they stay aligned because they're still linearly proportional to each other. And whether if I add more or less, it doesn't really change. Well, I still have the diagonal. But wait, I have two different boxes. How come the two different boxes are generating the exact same amount of the exact same random numbers? I thought random numbers were random, right? Well, it turns out that the problem is that for these numbers, for both boxes, I am using the same default seed called number 2. And here also number 2. And if I were to change it with one and with the other, you can see that now I have random numbers here, and now I do have random numbers here, except for the moment where the seed is the same for both of them. What? But then, what is this concept of seed that you're talking about? Let's take a look at actually how random numbers are generated computationally. I like this one. I'm going to use this one. uh, Let me start by some foundational notion about random numbers in computer science. It turns out that, as you can see on this meme, if you ever follow the Big Bang Theory, it's an amazing show. You should definitely check it out. It's very nerdy. And it turns out that it is true, as the meme says, true, real, random number generation using computers is a problem that still remains unsolved as of today for computers. Computers cannot really, for real, generate random numbers. And why is that the case? Well, think about it very, very conceptually. Computers are really good at computing things, aka taking some initial data, processing that data somehow, and churning out derived data. However, computers generating a random number conceptually means without any input data, without any reference, or without anything that is driving that generation, purely create a random number from scratch without no reference to anything before. If you think about it, that is probably one of the most creative processes that can be conceived. The generation of something out of absolutely nothing. And then that turns out to be computationally a huge problem. Such a huge problem that it hasn't still been solved today. And there's no prospect of that ever being solved. Because again, computers are really good at processing data based on some original data. They're really bad at generating stuff from absolutely nothing. That is, again, a very creative process if you think about it that way. So how do we then generate random numbers? Well, if we want to generate real, true random numbers, there are some techniques that are fairly modern, actually, that high specialized computation environments use. So, for example, it's very common to use atmospheric noise as a way to drive the generation of random numbers. And actually, if you go to random.org, one of the most common tools online for generating random numbers, it uses atmospheric noise here. Just because there is like these sounds that are in the atmosphere that vary, that fluctuate, and it turns out that statistically they can be used to generate pseudo random numbers. Or for example, there's this company called Cloudflare in San Francisco that is very well known for having in their headquarters, having a wall of lava lamps like these ones with cameras pointed at them and then measuring how the lava moves up and down and then using that to generate random numbers that they use for cryptography service that they sell. Because they need a lot of random numbers to feed new cryptographic keys for their encryption services. So when you need like real true random numbers, you use things that are inspired somehow by nature, and you use that inspiration so that it cannot be predicted mathematically or with an algorithm. But for not so professional or not so, for more like, like daily use for simpler things that don't threaten anyone's security or bank's accounts, then there are actually simpler methods to use. It turns out that the generation of random numbers in computer science is typically done with a series of equations or a series of expressions that have been proven to generate sequences of numbers that statistically seem random. So, long story short, their random number generation can be done with expressions, so either equations or polynomials or ways of generating sequences of numbers that look, for example, something like this. That they take an initial value and then they start generating sequences by using a fairly complex expression, if you will, and then these equations have been proven to generate sequences that statistically are random because they have even distributions of outcomes across a domain, right? Now, one of the consequences of this process, one of the consequences that in order to generate random numbers computationally, we use algorithms, we use an expression that is fairly complicated, but it's an expression. First of all, that is very unsafe if we use that for cryptography or for security. That's why we have the lava lamp situation, because if somebody finds out what the algorithm for generating random numbers is, then you're basically screwed. But, but the other consequence is that the numbers that we generate with these expressions are pseudo-random. And they are pseudo-random because they always start by a given number that is typically called the seed. And then what they do is that they operate with that number over and over again, or with derived numbers from that initial one. And it turns out that for any particular seed, so for any particular starting value in the calculation of random numbers, these expressions generate pseudo-random numbers because for the same number, for the same seed, they will always generate the same sequence of random numbers. So if I give this particular expression, if I start with the seed of 0, I will always get this particular sequence of numbers. If I start with the value of 1 for the seed, I will get a different sequence of numbers. But if I go back to a seed of 0, I will get the original same sequence of numbers as before. Because again, these sequences rely on some input, which is typically the seed, and then they manipulate that seed in order to generate sequences of numbers. So if they always start from the same seed, they always will generate the same sequence of numbers. So that idea that there is a seed or a one initial number that drives the generation of the random numbers is paramount to the way we generate random numbers, because what it means is that random number generation is deterministic. And when I say deterministic, I mean that it can be predicted based on the seed number. If we know the seed number and if we know the algorithm, then we will be able to actually generate the numbers ourselves. So for the same seed, we will always be generating the same sequence of random numbers. And because we were using the defaults here in Grasshopper, that's why we were getting the exact same numbers for this box and this box, because these are not looking at the atmosphere or any lava lamp. And therefore, the only thing that I need to do is I need to give each one of the random number generators a different seed. And with a different seed, I will generate different sequences for the x coordinates and different sequences for the y coordinates. And now we have something that looks way more like a random distribution of points in a two-dimensional space. I can extend this same idea to 3 dimensions by just copy and pasting this guy here. I still have the domain, I still have the same number of numbers, but I use this as the seed value, and you can see how they're all in a plane now because I'm using the same seed value for y and for z. But if I now change the seed, you can see how the points are now evenly distributed, or like randomly distributed in a box that is 10 by 10 by 10. Let me actually draw that box from a domain, and I have the domain here, the other domain here, and the other domain here. But I have the points, and these points are now randomly distributed inside of this box. And if I place some spheres in here, then I can see the points. The spheres. I can see the sphere. Oh, that is not. I can see the spheres a little more. Well, I cannot see the spheres. So no spheres. I like this better, like this. Okay. All right. What else do we need to talk about the random numbers? Sometimes if you look at the random number generation, you can see that in the case of Grasshopper, and this is specific to Grasshopper, the way we have generated the numbers here, these numbers do have all decimal part. And then it will be very often the case that we will want to generate integers that are also random. So how can we do that? Well, you might feel inclined to say, all right, let me copy all of this, and then I'm going to generate like, I'm going to generate all these random numbers here. And then in order to figure out how many numbers do I have here, in order to generate integers here, what I'm going to do is that I'm going to just round these numbers up. Okay. So for example, I can go to math and I can go to I forget what it is. Is it here polynomials? No, I think it's here is rounding. Yes. So in utilities, you have a component that rounds numbers and then rounds numbers, and it gives you n, the integer that is nearest to x, then the floor, and then the ceiling. So if I take n, you can see that I can have here 7, 8, blah, 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 whatever, which looks okay. It looks randomish. However, make sure that you never do this because, for example, let me show you what would happen if we generated. So let me show you first a way of figuring out how many elements do we have in here. So if I want to know how many zeros, how many ones, how many twos, how many threes I have in this random list, a technique that I can use is I can go to another tab that we haven't seen yet. So in sets, I can go to sets. And then here, what I can do is I can take a look at the member index. So that, is it member index? Let me double check this. Yes, it is member index because this component tells me the amount of times a specific member is found in a set. So I'm going to drop this here and I'm going to say, well, in this one, in this list of numbers, how many, this is the set that I want to figure out, how many, I need to also give it the members that I want to search for. So I'm going to generate a series of numbers that is going to go from 0 to the number 10. Okay, so that I need to give it 11 elements so that it goes from 0 to 10. And then if I fit that in, you can see that what I need to do is I need to make sure that I first convert these numbers that have decimal part. I need to convert them to an integer. And then as I do that, you can see that what I get in result is a tree that tells me, oh, this is nasty. The number of occurrences of the member. Sorry, this one, yes. The number of occurrences of each one of the members. So you can see that this list has apparently, for example, it has the number 0 is not present. Number 1 is not present. Number 2 is 1 time. Yes. Number 8 is 2 times. So here and here. Number 6 is also 2 times. Here and here. So with this, we can check how many elements are present in this random distribution. So one of the things about random distributions is that they are designed in a way that the numbers are sort of evenly distributed when it comes to really large amount of these values. So if I were to generate a 1 million points, for example, is that 1 million? Yes. If I were to generate 1 million numbers, I would expect that the distribution of these numbers, of how many zeros, ones, twos, threes, whatever, would be more or less the same. But if I do that, let me just crank this all the way up to 1 million. First of all, you see how my computer is frozen a little bit and it has taken quite a couple seconds to do. Then look at what is happening here. The random number distribution is kind of good because you can see that the number 1, 2, 3, 4, 5, 6, 7 roughly have the same amount of occurrences. So you have roughly the same amount of chances to get the number 0, 1, 2, 3, 4, 5, and 9. However, you see that number 0 and number 1 are roughly half. They are roughly half because when I was rounding these numbers, I was rounding to the nearest integer, which means that, let me do this in a diagram. Where is my mouse? If we say that we're generating random numbers between 0 and 4, for example, and we generate them at random intervals, if the rule that we use is rounding to the next integer, then basically what happens is that all these numbers that are here, all of these are going to round to number 1, all of these are going to round to number 2, all of these are going to round to number 3, but because there's no negative numbers or there's no numbers over 4, you can see that the amount of numbers that get rounded to 0 and to 4 is kind of half, because there's only half space in order to place those numbers. So that's why, for example, what it's typically done here is that instead of rounding numbers to the nearest integer, which is the regular way of rounding numbers, when we typically generate random numbers that are integers, when we round them, we use the floor rounding. And floor, what basically means is that no matter the decimal part, we're going to round to the lowest integer smaller than or equal than x. What that means is that if I go back to the diagram, now my diagram, instead of looking like that, it looks like this. All these numbers are going to be rounded to 0, which is the lowest integer. All these numbers are going to be rounded to 1. All these ones are going to be rounded to 2. And all these ones are going to be rounded to 3, which is the natural way of rounding. And each one of them will be more evenly distributed. So let's see if that is true. If I change this and I use the floor instead of the natural number, you can see that now we are at a more even distribution, but also check what has happened. Now we know that we don't have any elements rounded down to the number 10, because if 10 was the upper limit, then there's no possible rounding down to that number. Wait, but what if, these are random numbers. Is there a possibility that we would ever actually get the exact value of 4? Would it be ever possible to get the exact value of 4 and therefore this gets rounded down to floor? Is that a possibility? Well, technically it could be, because this is random numbers. You have equal chance of hitting a real number than not. Really. Well, that's not actually true. Don't quote me on that one. But technically you can. So it turns out that most random number generators that I know, what they do is that they ensure you that they can generate numbers for a given range. They can generate numbers that go from the initial value that you give them included. So they can generate a 0 in this case, but they generate numbers all the way up to the upper bound excluded. So they guarantee that you will never get a number 4. And that is represented with this inclusive square bracket. That means that 0 is included in the domain. And this parenthesis means that 4 is excluded, that will never be part of the random number generation. And the reason for that is what you just saw here. The idea that you can use this to generate random integers with an equal distribution. And therefore, when you want to generate random integers, you need to generate numbers from 0 to the upper bound of the integer that you want to generate without being included. So if I want to generate random numbers from 0 to 9, my domain has to be from 0 to 10, because we know that 10 will actually never be included. Okay? This part, this integer thing, was a little bit perhaps more advanced, but keep it in mind, because you will run into this issue at some point in the future if you keep doing these things professionally or for fun or in your design life. I don't know. All right, so I think this is more than enough for a crash course on random numbers. Remember, random numbers can be generated very easily computationally, but they will always be pseudo numbers, at least within programming languages and without using external services that look at the clouds and the lava lamps. So there will always be pseudo random. They will always depend on a seed. And for the same seed, they will always generate the same series of numbers. And also this whole ordeal of generating integers and rounding down, which we already heard me. So we're good with that. Now shall we do a few hands-on exercises to see how can we tame and how can we control randomness for our advantage? Let's do a few of these, because this is going to be a super interesting topic. And like this video, subscribe to the channel. Maybe if you like it, if you don't, then just move on. Maybe don't dislike the video, but if you don't like it, just move on your life and forget about me and all those things. Okay, thank you very much. See you on the next video. How was that? Had you ever heard about random numbers? Had you ever been lectured, or had you ever discussed like computational generation of random numbers, the nuances of random numbers, and all that stuff? Oh, it's raining here. No. Okay. So what are we doing next? I'm going to do one exercise. It's going to be super simple, and then I'm going to call it a day, because it's Friday. It's 5 p.m. and I would like to go out and enjoy the rain, I guess, because it's not raining too bad. I may go for a run, actually, because it's pretty good. Do I want to go for a run? I think I do. Okay. Fine. So what are we doing for an exercise? Well, let me save this stuff here. So I'm going to save, this is going to be 8.1 randomness. Okay. We're going to save this, and I don't need this. No. And what are we going to do? I would like to do an exercise where we're going to take some geometry. We're going to take some geometry, and we're going to take some geometry. We're going to make a terrain. We're going to make a landscape, right? And then we're going to make a tree. And then we're going to, like a tree shape, and then we're going to populate the surface with a bunch of these trees. But to make it feel more natural, we're going to give them random rotations, and we're also going to give them random scalings. Yes. We're going to give them random scaling. So let's do that. So I actually have an example that I can reuse. Let me find that. Okay, I'm going to import a file. Ooh, I like this. And okay, so shaded. I don't like these like ISO curves. Appearances, colors, context menu, rendering, the view, display modes, in shaded mode. I don't want to see the ISO curve. Exactly. Yeah, there you go. There you go. And then for ghosted, I don't want to see them either. Can I turn that off? Display options, visibility of ISO curves. There you go. I like that. Nice. Gee. Mm-hmm. I'm going to I'm going to bring this in. Okay, so I'm going to set the surface here. And then I'm going to the landscape. And then I'm going to take the line. It's going to be a collection of lines. Set multiple lines. No, no, no. I'm going to clear this. I'm just going to I'm going to do that while I'm going to do that as we go. Bye. Bye. Oh. So I'm going to do that, and then I'm going to do that, and then what am I going to do? And then amount of, I'm going to set here a slider that is going to be the amount of objects, and I'm also going to set one that is going to be the seed, and okay, and then I will add more stuff later. Okay. So I'm going to start here. Should I start by drawing? I think I need to start by drawing stuff, right? So drawing some sketches. So, okay. So I guess we're doing that. Okay. All right. So one thing that I need to do is I need to generate random points. So I want to generate a bunch of random points. So if we remember that a surface does have an internal U direction and an internal V direction, and if we make sure that, for example, that is between 0 and 1, and here it's between 0 and 1, then what we can do is we can generate random numbers from 0 and 1 and then use those to figure out where those are on top of the surface, I guess. And then we can put some planes here, and then we can generate some, we're going to do just planes so that we can generate planes. And then once we have those, we will generate, we will put the trees on top of those planes. Okay, well, that's what we're going to do. All right, let's start simple. Let's start by the simple stuff, which is going to be having a surface, right? We're going to call this the landscape, the topography, whatever that is. And then what we want to do is that we have this kind of external geometry that is like a tiny tree somewhere that we have like really designed. And what we want to do is we want to populate that surface with tiny instances of this tree. And at some point we will give them some kind of random field to those, okay? So we're going to start with the simple, which is populating the surface with random locations of this tree. And then we will move them and rotate them, whatever, in a second stage. The first thing that we need to do is we need to generate random locations on top of this surface. Because it's an Earth surface, we need to remember that internally it does have these two directions, the U direction and the V direction. And if we were to know, or if we could force the domains in each one of those directions to be 0 to 1 and 0 to 1, then the problem of generating random points on top of that surface is reduced to generating two sequences of random numbers between 0 and 1, that's for U, and then another one from 0 and 1 to V, and then getting from that surface the points in Euclidean world coordinates XYZ that correspond to a particular location in U and V. So what we're going to do is we're going to generate those random numbers and then find those points on top of the surface. And once we have them, we will just place XY planes because we're not going to incline the trees. Trees sometimes grow inclined to the normal of the surface, but in this case, it's not really a thing, I don't think, so we're not going to do this in this case. And then we will just do a simple reorientation operation to place all these trees on top of the surface. Now, I have gone ahead and inside of Grasshopper, I have generated a surface that kind of looks like a landscape. It has valleys and it has hills and that kind of stuff. And then I've also generated myself this kind of like wireframe sort of tree, which is just basically a collection of lines. It could be something a bit more elaborate, but I just wanted to do something simple. So what I'm going to do is I'm going to bring in the surface here. I'm going to bring it, and then I'm going to bring all those curves. I'm going to set multiple curves, and I'm going to select all of these guys here. And then you can see that now I have the collection of the 13 curves that work here. And then I'm going to click on a reference point that is at the base of my tree. I will use that to locate the first plane that is going to be used as reference for reorientation. So what do I do next? The next thing that I'm going to do is, as I said, we need to generate random numbers. We need to generate random numbers between 0 and 1 so that we can find the points on the surface that correspond to those u and v coordinates. So what are we going to do? So if I know that I want, for example, 165 trees, what I would like to do is I like to generate 165 random numbers between 0 and 1. So I'm going to go to sets, sequence, random, and then first I'm going to generate the first set of numbers. I'm going to use the default domain from 0 to 1. I'm going to generate 160 numbers, and the seed that I'm going to use for this is going to be this one, for example. Okay? And therefore, I get, for example, I'm going to keep it short for here. I'm going to just do, I don't know, 4 numbers so that it's a little easier to read. And then I have those 4 numbers that are random from 0 to 1. Those can be the random locations on the U domain of the surface. I can copy paste this and then create another set of random numbers for the V direction. However, remember, because I'm using the same seed, then I'm going to get the same numbers. So a very common trick to avoid always using the same seed is saying, well, whatever seed you give to this random number generation, use a seed for the other one that is the same one plus 1. So for example, I can do addition, and then I can add to this, I can add the straight number of 1. And that's going to give me a seed that is going to be different and is going to be enough to ensure that these two random lists are different. With that, I'm going to construct a point with these u coordinates and with these v coordinates. But remember, this is a little confusing. This point is going to have these x, y locations in C. Sorry, let me re-say that again. So the next thing that I want to do is I want to find on the surface points that have these u coordinates and these v coordinates. The way I can do that is by going to surfaces, analysis, and then evaluating the surface at a particular uv coordinate. So what does this do? It gives me information about the surface at these uv coordinates. So I can now plug in here the surface, and then in order to make sure that this surface has a domain from 0 to 1 in one direction and from 0 to 1 in the other, which could be very much not the case, and let me see if that's not the case. So I'm actually going to deconstruct the two-dimensional domain, and you can see that the first goes from 0 to 11 and the second one goes from 0 to 11 as well. So those are the domains of the surface. So in order to ensure that the surface goes from 0 to 1, I can right-click here and hit reparameterize. And what that will do is it will change the domains of the surface to fit them from 0 to 1. And now what I need is UV coordinates to evaluate. And you're seeing that what I'm being asked there for is for this, in the hexagon icon, it's a point, right? So what I need to give it is points. So that's why I need to construct a point. However, keep in mind that as I construct this point with these u and v coordinates, I'm going to be getting these actual points in this world, x, y, and z. But what this is actually not the way it works. So this is useless, because what this component is going to do is it's going to take these numbers and it's going to read x as if they were u coordinates and v as if they were v coordinates. And you can see that immediately I'm getting these 4 planes that I'm going to actually deconstruct into points. So I'm going to deconstruct and get the origin, and I'm just going to keep the points there. Okay? Look at what would have happened if I had not reparameterized. You would see that the values, the points, are concentrated in this area, which is because the domain goes from 0 to 11. No matter how many points I create, they're all going to be like randomly distributed in this like tiny corner of the surface. So by reparameterizing, now the surface has a domain from 0 to 1. And now I can use these points to place horizontal planes, so XY planes, on top of those points. And what I can do now is I can reorient all the curves here on my input to those planes. The way I'm going to do that is by going to Orient. I need the input geometry, so that's going to be all these curves. Then the initial reference plane is going to be the plane that is based on the point that I'm using as reference here. So this is going to be this plane, an XY plane that is centered there. That's going to be the origin plane, and the target plane. Let me set this to the value of 10. And the target planes are going to be all those planes that are just generated on top of the surface. And if I do that, you can see that, let's see what happens. I'm going to hide this, and I'm going to highlight the surface, and I'm going to highlight these points, and you can see that what is going on? I'm only getting branches in the air. I'm getting branches in the air here, branches in the air, branches in the air, and this other one has like 4 branches for some reason. Why is this happening? Well, what do we think might be happening? Whenever we have problems, we don't know what's happening, it's probably a matter of data. Okay? So what is happening? All the original planes all the target planes are on a list that has 10 planes. All the curves are in a list that have 13 planes. 13 curves, which means that when they get combined here, the first line goes with the first plane, the second line goes with the second plane, the third line goes with the third plane, and that's why it's not working out. So something that I can do is, because I want all of these curves to go with each one of these planes, what I can do is I can just graft these planes, okay? And then as I plug them in here, now each one of the planes has this has the tiny tree on top of them. And if I now populate this a lot, and I remove all these points and I clean things up a little bit, you can see that now the trees are looking much better. Okay, so I have been able to populate the trees on top of the landscape, but as you can see, because they all have the same size and the same orientation, they look super artificial. So can we improve this to make it look a bit more natural? Of course we can, and of course we're about to. All right. Hi, Dari. Oh, yes, you caught us by the end of a recording session. I think the best thing that you can do is you can go to our playlist, Introduction to Parametric Modeling, and start watching videos from there to catch up to where we are right now. Hidaki. What else? Yeah, so how are we going to do that? So I'm going to group things a little bit here. Okay. So these are going to be the points. And then these are going to be the generation of the planes. Okay. The first thing we can do to make this feel a bit more natural is to take each one of the trees and rotate it randomly between 0 and 360 degrees. So that is actually going to be super easy. It's going to be as easy as generating a list of random numbers between 0 and 360, and then using those to rotate each one of the planes before we to rotate each one of the planes before we do the translation. Okay, so piece of cake. I'm just going to generate a random set of numbers. How the domain is going to be from, and I'm actually going to hard code this. It's going to be from 0 to. Actually, no. Let me do this. Let me construct a domain. Let me construct a domain, and the domain is going to start at 0, and because it's going to be angles, the end is going to be 360. However, because we are starting to be a little more pro here, what I would like to do is I would like to work directly in radians, because rotations in Grasshopper always are handled in radians. So 250 360 degrees are 2 times pi, which I can write here as an expression, or I can just write as 6.28, 50 something, 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 which, by the way, equals to tau. And if you believe in tau, you should check tauday.com, like many of us righteous people. Let me not get into that. Okay, so that's going to be the value of 2 pi. So this is going to be a domain that goes from 0 to 2 pi. And then the number of random values is going to be equal to the number of trees. And then that generates a sequence of numbers between 0 and 6.28. And then what I can do is, maybe before grafting the trees, or for no particular reason, just because we have the numbers here flattened, so I can rotate this plane around its normal this many numbers. We could do this with transformation, so we could rotate an object inside of a plane. So for example, I can do, what is the geometry that I want to rotate? I want to rotate these planes. What are the angles? The angles are these angles here. And what is the rotation plane? The rotation plane is actually the plane itself. So I'm going to do that here. And you can see now how the planes have random rotations, and then if I plug those here down in the definition, now I'm going to turn these planes off, and you can see how the trees now have these random rotations that make them look much more interesting. Okay, and all right, and what is the next thing that I would like to do? What I would like to do is, trees are always not the same size, so what I would like to do is I would like to scale them up or down a tiny bit so that there is some difference between their sizes. So what I can do is I can say I can scale them, for example, and I'm going to scale, what is the geometry that I want to scale? This one. What is the center of the scaling? Is going to be each one of the planes, and this component already takes the center of the plane, and you can see that the factor is going to be 0.5. So you can see how automatically it's generating trees that are smaller. So what do I want to do? I think the way that I want to define this scaling is that I would like to say, I would like to set a factor for how big or how small they go. And if that factor is 1, then all the trees are going to be the exact same, are going to remain the same. But if I say the factor is going to be 1.2, then the domain should go between, I can just do that manually. Okay, so for example, let's say that I do, for example, 10, and I'm going to say this is the minimum scale. And I'm going to set this to 0.8, for example. And I'm going to set another value that is going to say maximum scale factor. And this is going to be 1.2. If I construct a domain with that, I construct a domain. What is the domain? I'm going to construct a domain with these two. And then I'm going to use that to generate another sequence of random points with this domain and with this many values, the values, how many trees I'm generating. You can see that I am generating factors from 0.8 to 1.2. And if I do those here, then I am getting weird stuff because of the structure of the data. So I just need to graft these to match the other grafted information. And then I can see that now the trees are now, can I see that? Sorry. Can I see that? Yes, you can see how some trees are getting bigger, some trees are getting smaller, and I can actually play with that. So I can play with changing the scale up of many of them, or just all of them, making them look very similar. Yeah. This is kind of cool, right? Okay, well, and then I think with this, I think we would be ready to go. Let me just bake this and see what it looks like. I'm going to bake this, and then I'm going to shut this down, and I'm going to shut this down, and I'm going to show all the geometry, and I don't know what that is doing there. And I'm going to render this and take a look. This looks nice, huh? How nice is this? So we have this like forest looking kind of surface now. All right, well, I think with this, that is where I wanted to leave it. So this has been the generation of a forest of vegetation on top of diagrammatic one, on top of a landscape. So I hope this was useful, and I hope this illustrated the use of randomness, the creative use of randomness. So thank you very much. Consider maybe liking this video or subscribing to the channel. And if you like what you saw, then maybe you will like what you will see in the next videos on this series. Thanks a lot, and see you in the next videos. All right, so I'm going to record the introduction, and I think we're going to be done for the day. It's been a long day. Okay. And what is this going to be? Landscape with random. Hi, this is Jose Luis, and welcome to another video on this series, Introduction to Parametric Modeling. This is going to be the first hands-on exercise that we're going to do to try out randomness and how it can help us create things that, for example, feel more inspired by nature and have that like randomness feeling that sometimes nature has. So this exercise is going to be about taking this topography or this landscape of whatever terrain and taking this one tiny wireframe tree that we have done, and we're going to populate that tree randomly on top of the landscape. And of course, we're going to control how many of these elements we want. So if a lot of them or not so many of them, we're also going to be given them a random rotation so that they don't look like they're all looking in the same direction. And at the same time, we will also give them some kind of random scaling so that we can just like have some of them being super small, some of them being much larger, and maybe this gives us like an increased feeling of that randomness. And once we have everything working, then things are going to look something like this kind of landscape of I don't know, random vegetation. I don't know. It's going to be pretty cool. It's also going to be fairly easy to do. It's going to involve just a few random numbers and some simple transformations. So no big deal about it. Okay, let's get started. Let's get some fun with nature-inspired parametric modeling. All right, I'm done for the day. Yoo-hoo, that was a lot. Oh God. How's everyone holding on? Did you like this exercise? Randomness can be fun, huh? Thank you, Rolando. Thank you. All right. So let me wrap the exercise up. I'm going to save the files. I'm going to make sure that people can check this out in the future. And for example, yeah. No problem. And yeah, anytime. You know where to find us if you want more. Okay, so this file looks ready for action. I can save that. I can save this file here. I'm going to make myself a few annotations to remind myself when we do the editing. And in the meantime, does anyone have any questions, any things you want to talk about? And then it's going to be here. Okay. Wow, that was an intense afternoon. Oh, oh, God, that was a lot. Okay, we're almost done with the playlist. Are you not excited? What we have left, which we will finish next week, is going to be a couple more exercises. A couple more exercises using randomness. A couple more exercises using randomness. Then we're going to do a few examples using meshes, and then we're doing a couple examples using images. And with that, I think that's going to be the playlist. So hopefully we can wrap this up in the first couple days, 2-3 days, because I'm going to be on vacation on Thursday. So hopefully, yeah, we have to finish that up before that. All right. All right. Thank you, Hania. I think I'm going to call it a day. It was wonderful to spend the week with you again. Thanks for being here. You make my life shine by being there and knowing that I'm talking to human beings while I'm doing this. And I hope you have a wonderful weekend, whatever that may find you. See you on Monday in the morning, probably. I will, I still haven't scheduled them, but as soon as I decide when we're going live, I will schedule the videos on the channel so that you can see them. And then you can see, and then I will schedule them. You will also, I will post something on our Instagram of when we go live, but also you can subscribe to our Google Calendar, which is somewhere on the chat. I think I posted it on the chat. I didn't post it today. Damn it. Okay, so this is the Google Calendar. I just posted it on the on the channel. And if you want to be in communications or have conversations throughout the week, feel free to join our Discord server. There's a link on the description of this video. I just posted a link on the chat. And yes, Rolando, we can connect via the Discord server if you're interested. Goodbye, fellow human beings. You are right. And all right. And thanks a lot. Have a wonderful weekend. Bye bye, everyone. Ciao, ciao, ciao. Bye.